Hello, this is a video for Chapter 9 of Year 1 of the Applied course, and it's specifically for 9b, which is on velocity time graphs. Okay, in 9a you looked at displacement time graphs, where on the y-axis it was labelled S for displacement. Now we've got V for velocity. It's really important that you look carefully at that y-axis when you're looking at mechanics questions, because it tells you more about the context of the question and you can interpret it properly. Okay, so in this first graph here, the blue line represents the journey of an object, and it starts at 0 and it ends at 0 after a certain amount of time. So we can say in this graph here, the object is stationary. Okay, in the next graph, we have it starting at a velocity of u over a certain amount of time. We've got a horizontal line, so it's staying the same, and it ends at a velocity of u. Okay, so it's staying the same velocity, so we can say this is a constant velocity. So a horizontal line is a constant velocity, not stationary as it was in the displacement time graph. In this third one here, it starts at a velocity of u and it ends at a higher velocity of v. So we can say that it's accelerating, but we can say more than that because it's a straight line. It's accelerating uniformly. Uniformly means at the same rate. Okay, let's consider the gradient. So to work out the gradient of the line on this graph, we would look at the change in velocity and we divide it by the change in time. Okay, in differentiation, you might use this sort of terminology, dv over dt. And this is all equal to the acceleration. So if you find the gradient on a velocity time graph at any particular point, you can work out the acceleration at that point. Okay, let's consider a couple more graphs. So what would be happening if the graph looked like this? So here's my velocity, here's my time. Well, it's not a straight line anymore. However, the velocity is increasing, so it is accelerating, but this time it's accelerating at an increasing rate. Okay, the acceleration is getting higher as it goes along, so it's not uniform acceleration. Okay, final little graph to look at. So in this one here, we've got a negative gradient. So we can say that it's accelerating negatively, but that's better known as deceleration. So in this graph here, the object is getting slower at a uniform rate because it's a straight line. One other thing to consider on this particular graph here is because this is zero velocity, at this point here, it is actually stationary. It is stopped. As it goes below, we've got a negative velocity. So that means relative to the starting position, it will be coming back towards that starting point. Okay, so this one here, it's got a velocity which is moving away from the starting point. Here it stops, and here it is moving back towards the starting point. Okay, now that one modelling assumption that we're assuming there is that the velocity time graph represents the motion of an object travelling in a straight line at a constant velocity. If we're doing these types of velocity time graph, we need to assume that because then it's relative to displacement. So looking at this graph here, we have a constant velocity over a certain amount of time. So the velocity is v and the time is t. Let's consider what the area means on this graph. So the area underneath the graph is equal to v times t. Okay, so if we think back to our displacement velocity time formula that we looked at in the previous chapter, velocity is equal to displacement divided by time. Now, if we rearrange that, we can rearrange it to S is equal to velocity times time, which is the same as my formula up here. So we can say that the area is equal to displacement, assuming that it's travelling in a straight line. Okay, so the area underneath a velocity time graph, you can work it out. It gives you the displacement of the graph, so the total distance in terms of displacement. Okay, let's move on to some of the examples from the textbook. The figure shows a velocity time graph illustrating the motion of a cyclist moving along a straight road for a period of 12 seconds. So that's important. It's moving along a straight road. T is 12 seconds here, so that's there. For the first 8 seconds, he moves at a constant speed. So obviously we can see that flat horizontal line there. And she then decelerates, so it's got the negative gradient at a constant rate, so it's a straight line uniformly, and it stops after a further 4 seconds. Okay, so find the displacement from the starting point of the cyclist after this 12-second period. Okay, 2 ways we can do that. We'll do it very quickly. We could split it into different shapes, and we can work out the area of each of the shapes. So the first one, A, is equal to 6 times 8, which is 48 meters. And B is equal to, right, so the base of this triangle is 4, the height is still 6. So 4 times 6, because it's a triangle, divide it by 2. That will be 12 meters. So the total displacement is equal to 48 plus 12, which equals 60 meters. Okay, now we can do it that way. However, in this particular case, it's a slightly inefficient way of doing it. You can see we've actually got a trapezium. So the trapezium, formula for the trapezium is A plus B over 2 times by H. So in this case, A is the distance across here, so that'll be 8. B would be the distance across there, that's 12, so 8 plus 12 over 2 times by the height of the trapezium. So in this case, the height is 6. And we can work that out. 8 plus 12 is 10, 20, divided by 2 is 10, 10 times 6 is 60. So a much more efficient way of working it out using that trapezium. So if you spot a trapezium, use a trapezium because it's much better. Okay, B, work out the rate at which the cyclist decelerates. So remember, the deceleration or the acceleration is worked out using the gradient. So we need the change in velocity divided by the change in time. So in this case, it's gone from 6 meters per second down to 0 meters per second. So the change in velocity is 6. Change in time is 4. So we can work that out. 6 divided by 4 is 1.5. Let's think about the units. So the units here is meters per second to the minus 1, and we divide that by seconds. So that will be, that's wrong there. That will be seconds. So this would be meters per second to the minus 2. Okay, moving on to example 3. The particle moves along a straight line. The particle accelerates uniformly. So it's accelerating uniformly from rest, so from 0 to a velocity of 8 meters per second in t seconds. The particle then travels at a constant velocity at 8 meters per second for 5t seconds. The particle then decelerates uniformly to a rest in a further 40 seconds. Okay, so this is your typical problem-solving type question for this topic. So we need to draw ourselves a graph. Even if it doesn't say sketch a graph, it is always a very good idea in anything we do in mechanics and lots of aspects of statistics as well, as you would have found also in your pure maths. So it starts, so our y-axis is the is the velocity, and the x-axis is time, and it starts from a velocity, which is black, of 0 because it starts from rest. It accelerates uniformly, so it's got a straight line. It then goes at a constant velocity, and then it decelerates over a certain period of time. Okay, we need to label this graph. Okay, you can't just leave it like that. We do need to label it. So it starts from 0 and it goes up to 8, and at this point here, that has taken t seconds, and it's then gone at a constant rate for 5t seconds. So this bit up to this bit here is 5t. So this at this point, the t plus the 5t is 6t, and then it decelerates for a further 40 seconds to this point here. Okay, we've sketched the velocity time graph. We now need to, given the total displacement is 600, find the value of t. So we can substitute this into a formula. So this is a trapezium again, and we've got two parallel sides, and we know what the distance of that is, and we know what the distance of that is. So our 600 meters displacement is equal to the area of this trapezium. So the area is A plus B over 2 times by H. The A is equal to this, that is 5t. The B is all the way across here, so it's 6t plus 40. All over 2, multiplied by the height, which is 8. So you can work this out. So 11t plus 40 over 2 times by 8. So that's 5.5t plus 20 times by 8. 44t plus 160. Let's bring the 600 back in here. We can then solve this as an equation. So the 44t is equal to 600 take away 160, 440. So t is equal to 10. Think about the units. Well, we had meters per second there and seconds here. So the unit of distance is equal to meters. And that is